All right, kids, so let me kind of paint the big picture about where we're at, historically and logically. So, Copernicus publishes work, says, hey, we live in a sun-centered solar system. That wasn't so cool, because, you know, we wanted to feel like we were special. So here's the analogy that I can give. It's just like, let's say for every day of your school, your mom packs your lunch, and she includes a little note that says, you're special, love you, you know, all these things, okay? Very, you know, a letter that affirms that you're something unique, okay? And then on the last day of your senior year, you get a note that says, I was kidding, you're just like every other kid. You know, it's just like, that's kind of devastating, you know? That's harsh, you know? And so, but that was kind of the mindset when we realized we're just like all the other planets and we orbit around the sun. You know, it's like, we're not all that in a bag of chips. So it was kind of deflating to our collective egos. So Tycho Brahe goes along, you know, he's got his own island. There was this amazing the mechanism to record all this data. He has decades of it. Johannes Kepler comes along, steals the data, goes back, formulates his 3 laws of planetary motion. Okay, and so this is where we're at right now. So Kepler really didn't try to explain why it happened. He was just kind of like a reporter. He goes, here's the news. They move in ellipses, they sweep out equal areas and equal times, and the third law was this ratio of period to radius. Now, if God really wanted to make this simple, there would have been a 1-to-1 ratio between distance and period. So like if Saturn is 5.4 times further out from the Earth, Saturn's orbital period would have been 5.4 years. Okay? If Jupiter has an orbital period of 12 years, it would have been 12 astronomical units away. Didn't quite work out that way. But it wasn't bad. At least it was just period squared and radius cubed. Okay, but again, Kepler was doing all this by hand. He had to crunch through all of Tycho's data, but he got it. So this is in the late early 1600s. Okay, so this kind of give you a time frame on it. So Isaac Newton comes along in mid to late 1600s, so about 50, 60 years later. Okay, and he says, okay, hey, let's talk about gravity. And you know, everybody has heard this story about, an apple fell on Newton's head and he invented gravity. It's like, let's just think that story through. Really? He invented gravity. Like, gravity didn't exist before then, and then all of a sudden, wow, now there's gravity. He has a patent on it. No, okay? No. Well, the story was that when the apple fell on his head, he realized that the same force that made the apple fall on his head was the same force that made the earth fall towards the earth, made the moon fall towards the earth. But the moon was just a lot further away, so that gravitational force was a lot weaker. So Newton comes up with this law of universal gravitation, and it's F equals big G, M1, M2 over d squared. And if you're talking about like a radius, okay, like for example, we're going to eventually equate centripetal force with gravitational force. So sometimes you'll see it written as big G M1 M2 over r squared. Okay, so if it's r, that's just a radius. Okay, d is just a distance between 2 points. Right, so basically it's the same thing. So let's talk about that value of big G. And that's 6.67 times 10 to the negative 11 newtons meters squared over kilograms squared. So if you look on your equation sheet, okay, so up here at the top, there's this value of big G, and there's also the mass of the Earth and the radius of the Earth. So what I would recommend is that this is a number that we're going to use a lot, okay? I would recommend that you store that number in like a memory cell of your calculator, okay? You can all do that. It's like, there should be like an STO function, okay? And I'd store that as big G. But when you do that, don't type in the times 10. Go like 6.67 and then hit that EE key to the negative 11th. Because if you type in times 10, sometimes it really messes up your order of operations and you get answers that don't make any sense at all, okay? So that's a number that you're going to need a lot. We're also going to use the mass of the Earth a lot and the radius of the Earth a lot. So if you're storing numbers, you want to go ahead and do that. You could store those three values up here in the top left: mass of the Earth, radius of the Earth, and big G. So here's how this works. So let's say we started with Kelsey yesterday. So here's Kelsey. And yesterday I drew her with her hair down. Today I've got her draw her with her hair up in a bun. Okay? Okay? So there's Kelsey. All right?
Looking good.
I know, they're top heavy. You know, it's like, it should be like, whoa, okay? All right? So let's say that Kelsey, with all that hair, has a mass of 50 kilograms. Okay? And 5 meters away, over there on the wall, there's a fire extinguisher. And that has a mass of 2 kilograms. And they are, I don't know, 4 meters apart. Let's do that. Okay? So I want to calculate the gravitational attraction between Kelsey and the fire extinguisher. Okay? Now, let's talk about this equation. So the only thing that you have to calculate the gravitational attraction between two objects. Hello.
You don't have it. Calcium chloride.
Huh?
Massive container of calcium chloride.
Oh God, no. Yeah.
Okay.
I never use it.
I didn't think you did, but
I understand.
you all, and I'm on a scavenger credit. So.
Okay. Good luck with that. So the only thing you have to calculate the gravitational attraction of two objects, the two masses, and how far apart they are. Okay, that's it. So what this means, and here's like the ramifications of this, is that you cannot ever be in zero gravity. So what that means is that Kelsey is attracted to that fire extinguisher. Okay, and we're going to do the math here and we're going to get that value. She's obviously attracted to this big rock that we're on. Okay, she's attracted to the moon, to the sun, to Saturn, Jupiter. Every bit of matter that makes you up is attracted to every bit of matter that exists in the universe. Okay, so this is this kind of kumbaya, oh, we're all one kind of equation. Okay, so the only way that you can be technically in zero gravity, and this is like the ultimate freshman situation, the only way that you can be in zero gravity is if you are the only thing that exists in the universe. Okay, because if there's anything else, you're going to be gravitationally attracted to that. Okay? So when someone says, oh, they're floating in zero gravity, and I was like, oh, shut up. Okay? No. No. It's horrible. Okay? No. Because you can't even orbit in zero gravity, because if there's no gravity, you're just going to fly off in a straight line anyway. So that's the first thing I want you to get through. You are gravitationally attracted to everything in the universe. So let's do this calculation. Now, before you touch your calculator, I want to get what's called an order of magnitude. Okay. So this unit, more so than any other unit we're going to have, you have the potential to get answers that make absolutely no sense. Okay. Like for example, my AP Physics class, they took the test yesterday over all this planetary motion stuff. And I've seen this before. They have to calculate how long, and you guys will too, it's how long it takes for the Lunar Command Module to orbit the moon. It should take about 90 minutes, okay? I got an answer literally, I did the conversion. This answer was literally longer than the universe itself has existed, okay? And you all giggle and go, Mr. Burkamp, we won't do that, you lie, okay? So,
Can you say who?
huh?
Can you say who?
No, won't do
It's
it.
probably Brady.
So,
Probably.
So here's the point. Your calculator is going to give you answers. But if you don't look at your answer and go, wow, does this seem reasonable? You're blissfully going to write down an answer, and then I'm going to go, really? You're traveling faster than the speed of light, or you're going to orbit all the way around the Earth in 0.05 seconds, okay? So I'm just telling you, you have the potential, more so than any other unit we will do, to get answers that make no physical sense whatsoever, because it just depends upon how you punch them into your calculator. So the kid had all the numbers right. He solved the equation beautifully, but just punched something wrong into the calculator and just got an answer that made no sense. So here's the deal. So this is going to be 6.67 times 10 to the negative 11th newtons meters squared over kilograms squared times 50 kilograms times 2 kilograms divided by 4 meters squared, okay? And again, I just want to get an idea of what this answer is going to be, what's called an order of magnitude, okay? So if you look at this 6.67 times 10 to the negative 11th, and we'll talk about where this number comes from when we get done with this calculation. For now, just accept it, okay? And if you notice the units, this is newtons. Wow, that was loud. That was newtons meters squared over kilograms squared. And it has those units because you have kilograms times kilograms, which is going to cancel out those kilograms squared. And then you're dividing by meters squared, which is going to get rid of those. The only thing you have left is newtons. And so that's what that force is going to be measured in. So if I take 50 times 2, I get 100, right? Okay, which is 10 to the second. This is what we call an order of magnitude. We're just going to look at exponents. So when I take 10 to the second and multiply that by 10 to the negative 11th, so let's review our exponents. So I'm going to take 10 to the negative 11th and multiply that by 10 to the second. So when you multiply exponents, do you add or subtract? Add. So if I take 10 to the negative 11th times 10 to the second, I should get 10 to the negative 9th, right? Now, 4 squared is 16, right? So that's 10 to the first. So if I take 10 to the negative 9th divided by 10 to the first, I should get 10 to the negative 10. So this gets me a ballpark estimate, okay? It just kind of shows me, hey, this is where I should end up. It might be 10 to the negative 11th, it might be 10 to the negative 9th. It's going to be somewhere in this ballpark, okay? So if I do this calculation and I get like 10 to the third, I've done something wrong. If I get 10 to the negative 20th, I've done something wrong. So order of magnitude just gives you an idea of what this answer should be. So now, somebody actually run the numbers. So basically, it's 6.67 times 10 to the negative 11th multiplied by 100 divided by 16.
4.17.
What'd you get?
4.17 to the negative 10.
4.17 times 10 to the negative 10th newtons. Okay? It's cool. Now, so there's a lot of things I worry about when I teach. Okay? Are you guys going to learn it? You know, does my hair look okay? There's a whole bunch of things that I worry about, right? Is it going to get frizzy because it's going to rain today? That's a legitimate concern. Okay? I'm just saying, Kelsey. I just made that up.
Yeah.
And that's not relevant at all to
No.
anything we talked about this morning.
No.
So, but one of the things I'm not going to worry about is that fire extinguisher at some point in my lecture start to drift off that wall and, you know, come off the wall and start to drift towards Kelsey. Okay, it would be really, really weird, okay? So that isn't one of the things that I'm going to worry about, okay? Because, yes, there is a gravitational attraction between Kelsey and the fire extinguisher. There is, okay? But it's really, 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 really small, okay? So, and the other thing I'm not going to worry about is Kelsey starting to drift towards the fire extinguisher, which would be even weirder, okay? So it's there, but it's just really, really small. It's not going to impact your daily life, okay? It's such a small value. So if you look at what Newton did, Newton was a big idea kind of guy. He didn't get bogged down in the details. So Newton actually never came up with the numeric value of 6.67 times 10 to the negative 11. He just said it's just a constant of proportionality. actually came up with that number was a guy by the name of Henry Cavendish. He was a British scientist. And so what Cavendish did, it was really clever. He actually had a room built on his house for this experiment because his equipment was so sensitive. He was afraid that his own mass would influence the experiment. So he didn't want to be in there because he was afraid that he would affect it. So basically what he did is that he took a big wire and he hung 2 lead spheres from each one. So there was like a bar, and then you had the lead spheres that hung down. And this is what was called a torsion wire. And he knew how much force it took to make that wire twist. So that was the initial setup. So then what he did is that he brought in other lead spheres close to him. And when he did that, this wire would twist just a little bit, okay? Just not a whole lot, but it would twist just a little bit. And these had to be massive to get this effect that he could notice it. So what Cavendish did is that he went back up to this equation. So he knew how much the wire twisted. So he knew how much force that took. Oh, so he knew force. He knew the mass of the spheres that he used, so he knew these 2 values. He knew how far apart they were, so he knew the distance, so he was able to solve for big G. Okay? And later on you'll see why this works. Once he got that number, he was actually able to use that number to determine the mass of the entire Earth. Okay? Which was kind of cool. So Cavendish claim to fame was he was the first one to like weigh the Earth and find the mass of the Earth. But we'll get into that later. Okay, so at this point we've got a pretty small force. All right. So, but Kelsey goes, you know, I really like that fire extinguisher. It's just kind of cool. So Kelsey's going to get up and she's going to walk towards the fire extinguisher. All right. So Kelsey's going to walk to the fire extinguisher, and when Kelsey gets closer to the fire extinguisher, we're going to cut that distance in half, okay? So now Kelsey is going to be 2 meters away from the fire extinguisher. Now, when we do this calculation, Kelsey, you're now 2 meters away from the fire extinguisher. Are you going to feel more gravitational attraction or less gravitational attraction? More. Why?
Because you're closer to...
Yeah, it's more interactive, right?
Yeah.
So there's both of your gravitational fields are basically going to interact. So we're going to do this again. So we're still going to have 6.67 times 10 to the negative 11th, right? Newtons meters squared over kilograms squared. And then we're still going to have 50 kilograms. We're still going to have 2 kilograms. But now we're going to have 2 meters squared. Okay? So that's 4. So run these numbers again. So take 6.67 basically times 25, because 2 squared is 4. So take 6.67 times 10 to the negative 11th and multiply that by 25. And be thankful you have calculators, because doing these by hand sucks.
Oh, you're waiting on me.
Yeah.
I think I did something wrong.
Okay.
Wait, how'd you get 20
Well, 2 squared is
Oh,
4.
yeah, 'cause that's much
Okay.
Oh, okay, so I see.
So, 1.67 times 10 to the negative 9?
Times 10 to the negative 9th newtons. Okay? Now, so here's what I want you to do, Aiden. Okay? I want you to take 1.67 times 10 to the negative 9th, and I want you to divide that by that first answer of 4.17 times 10 to the negative 10.
4.
You get 4. So notice that her gravitational attraction is 4 times greater. Okay? So she reduced the distance by a half, okay? But the force became 4 times greater. Why?
It's squared.
Because it's squared, okay? So if you look at what happened mathematically, you had F equals big G, M1, M2, but then we had D over 2 squared, right? Because we cut that distance in half. We took 4 meters and divided it by 2, and we dropped it down to 2 meters. Oh, okay, cool. So that becomes big G, M1, M2, D squared over 4. The 4 flips up. It increases by a factor of 4. Okay? So this is what's going to be important. This is an exponential relationship. Okay? It's an inverse square relationship. So if we reduce that distance by a half, the force is going to go up by a factor of 4. Now, let's say the other side happens. Kelsey goes, that's just kind of weird. Okay? I really don't like the fire extinguisher. So she's going to get up and she's going to walk. And instead of being 4 meters away, she's going to walk way over here and she's going to be 8 meters away. So now we're going to double the distance between her and the fire extinguisher. So if we double the distance, what should happen to the gravitational force?
Decrease.
It should decrease by how much?
4.
By a fourth. So it's going to be a fourth as much. Okay? So if you double the distance, then you still have the same big G, same mass of Kelsey, the same mass of the fire extinguisher, but now we're going to have 2D squared, which is going to be like dividing by 4, so the force would be 1/4 as much. Okay? So here's what's important, because that's squared and you're dividing. If you reduce the distance by half, it goes up by a factor of 4. If you double the distance, it goes down by a factor of 4. Now, if she goes, I'm going to move like out to California. Like, I got to get away from this thing. Okay? She moves all the way to California. Is that force ever going to drop to 0?
No.
No. So no matter where Kelsey goes in her travels, she's always going to be gravitationally attracted to a fire extinguisher in an MG20. Okay? Which is true of all of you. Okay? So no matter where you go, it's like, oh, I feel melancholy. I feel the pull of the fire extinguisher. Okay? Because you're never going to get away from it. Like now you're going, man, Burkamp, that's just going to mess with me. It's like, okay, it's all right. Okay. Got this idea. Now, back to the lab. Okay? Back to the lab. So what we're going to do is we're going to try and figure out how the force of gravity between Mercury and the Sun changes. Okay? So we're going to kind of do this together initially. So go to that last page on the lab, and we're going to find D2, which is the point that's furthest away when Mercury is furthest away. So look, somebody look through that data table and find me the greatest value when Mercury is farthest away as it can possibly be.
7.467.
What was it? Point what?
467.
0.467 AUs. Then we're going to go to D1, which is when it is as close as it's going to be. What'd you say, Luke?
0.307.
AUs. Okay. So here's what we're going to do. We're going to figure out how that force changes as Mercury goes around. So here's what I want you to do. Here's this orbit, right? So listen to me. This is not the actual force, okay? This is a relative amount of force. So down there on number 5, you're going to go to the point where the Mercury is furthest away from this point in its orbit, and you're going to draw a vector 1 centimeter long, okay? And so what we're going to do is that we're going to use that as a baseline value. So this is not 1 Newton, okay? I am not going to keep Mercury in orbit around the sun by applying 1 Newton of force, okay? All we're saying is that this is a relative amount of force, okay? That's all we're saying. It's a relative amount of force. Because this is when the gravitational force is going to be the weakest. So why is the gravitational force weakest way out here? Yeah, and you're dividing by d squared, okay? So when Mercury is at, and this is going to be important, okay? When Mercury is at its furthest point, the gravitational force is at its weakest value, okay? Now, what we want to do is figure out when Mercury gets closer, we're going to try and figure out what that new amount of force is at that point, okay? So, what we're going to do is that we're going to use this ratio that I've given you on number 5, which is 1 over d1 over d2 quantity squared, okay? So, come in here, and we said d1 was 0.307, and then we're going to divide that by 0.467, and my phone's going to ring. So stop that camera for a second. We need to stop it anyway. Units, okay? This is just a ratio because that's AUs, that's AUs. So we're taking AUs and did you start the camera back up?
I started back up.
Okay, thank you. So this is AUs, this is AUs. The AUs cancel out. So this has no units, okay? This is not newtons. This is not force. This is just a relative amount of force, okay? That's all this is. So somebody take 0.307, divide that by 0.467, square that, and then take the inverse of it. What do you get?
2.31.
2 point what?
31.
2.31. So out of this, you get 2.31. So let me explain what this number means. When Mercury is at its closest point, relative to when it's furthest away, that force is 2.31 times greater, okay? Now, to give you some, let's put this in a little bit of perspective, okay? So let's say you make $10 an hour, okay? And your boss comes to you and says, hey, I'm going to increase your hourly wage by a factor of 2.31, okay? So you're going to go from making $10 an hour to $23.10 an hour, okay? It's a pretty hefty increase, right? So this is, but again, this is not newtons. All we're saying is that that gravitational force, when it's closest, relative to when it's furthest away, is 2.31 times greater. Okay? Basically more than doubles. Okay? So that's a pretty big change in that gravitational force. So here's what you're going to do. So then you're going to go to where Mercury is at its closest point, and you're going to draw a force vector 2.31 units long, okay, 2.31 centimeters. And that's just going to indicate at that point that that force is 2.31 times greater. Now, here's the other thing I want you to see. This is going to be important. We're focused on the pull on Mercury. But because of Newton's third law, to really do this right, and I'm not going to have you do this because your graph would just get horribly jumbled, but here's what I want you to understand. We should, by rights, come in here from the star and draw also a vector 2.31 centimeters long this way. Because Mercury is being pulled with this relative force that's 2.31 times greater. Guess what? At the same time, the sun is being pulled by Mercury with relative forces 2.31 times greater. Out here, when it's 1 centimeter away, we should draw a vector from the sun out towards Mercury, also with a relative value of 1. Okay? So everybody focuses on Mercury, which is cool, right? It is. But here's what because of Newton's third law, you have to understand that force is also being exerted out this way. Okay? It isn't just, oh, this is what Mercury is doing, but it's also what Mercury is doing to the sun. Okay, so here's what I want you to do right now. You're going to go and you're going to pick a couple other points, okay? I don't care which points you pick a couple points. And you're going to calculate the relative amount of force at those other points. And again, everybody's numbers are going to be different. So, what you're going to do is you're going to keep D2 as that constant, okay? That's at furthest one. So you're going to keep 0.467 as our baseline data. So you're going to go through and you're going to pick another date, okay? And you're going to say, okay, this is what that D1 is at that point. So you're going to take whatever that is, divide it by 0.467, square that, that's going to get you that new relative force, which obviously has to be less than 2.31, because that's when it's at its relative maximum strength. So come in here, pick two other points, figure out what those values are, and then you're going to come in here and you're going to draw those vectors on that graph. So you're going to show me this calculation here, okay? You're going to show me this one, where you take whatever that distance is, divide it by 0.467, square it, take the inverse of it, and then you're going to go to your graph and you're going to draw those lines. And draw them like bright enough, dark enough, whatever, so that I can easily see them. Even if you want to like take a highlighter and like circle around it so I can very easily see what those are. Okay, Ryan, stop, you're under camera. Okay, so now at this point, one of the great revelations of science takes place in terms of like how things fit together, okay? So if you look at what's happening in terms of the orbital path of Mercury. So we just figured out that when Mercury is closest to the sun, that force is 2.31 times greater than what it is when it's furthest point, okay? We're not saying it's 2.31 newtons. We're just saying it's 2.31 times greater. So when Mercury is closest, that's when it has its greatest gravitational attraction, okay? That's when it's closest. Boom, here you go. When it's furthest away, oddly enough, that gravitational force is decreasing. So first off, what you need to understand is that the gravitational force between Mercury and the sun changes as a function of distance, okay? It's going to be important. It's not a constant value. It's continuously changing because the distance is continuously changing. So we got that side of it. Now, is Mercury undergoing centripetal acceleration as it goes around the sun? Okay, I'll see you shake your head yes. Why?
I mean, gravity,
You mean gravity?
I don't know how to answer it.
Okay, can I help you out a little bit?
Yeah,
Okay.
always.
Kids say, no, don't help. Okay, so here's the deal. Could Mercury orbit the sun without centripetal force? No, okay. So something has to be providing that inward force, right? Something has to be providing that inward force. So either there's a really big rope between the sun and Mercury. Okay, there's a big massive cable that's holding Mercury in orbit. Okay, it's an option. There's like a track that Mercury is driving around, so it's like planetary NASCAR. Okay, it's an oval track that Mercury's driving around. It's an option. Or there's gravity. Okay, let's just go with the gravity option. Okay, so if this thing is undergoing centripetal acceleration, which it is, there has to be a force, because, Kelsey, if there was no force, what would Mercury do?
Fly off.
Yeah, go off on a straight line, okay? Mercury would just fly off in a straight line. So we know there has to be some amount of gravitational force. And we know that force changes, okay? And we also know it's undergoing centripetal acceleration because it's not moving in a straight line, okay? Now, we just learned that centripetal force equals mv squared over r, okay? So if you make that analogy as Mercury going around the sun, okay, instead of maintaining a constant radius, okay, I would always be changing that radius, make it further, make it closer, make it further, make it closer, okay? That radius is continuously changing, but it's still undergoing centripetal force. So here's the question. If this, is this going to be the mass of Mercury, or is this going to be the mass of the sun? Lily.
Mass of Mercury.
Beautiful. Why? Your answer is right.
I don't know.
Well, what's moving around in a circle?
Mercury.
Mercury is. Just like when we did the lab,
Oh, we did the stopper.
yeah, we did the mass of the stopper, not what was hanging down, right? Because that's what was moving. So this is going to be the mass of Mercury. Now, this is where Kepler joins up with Newton. Okay, we're going to merge these two ideas together. Okay, this is going to be important. So this is the mass of Mercury. As Mercury goes around in its orbit, is the velocity constant? Brian Bender.
Is the velocity constant?
Yes, as Mercury goes around that orbit,
No.
is the velocity constant?
No.
So when is the velocity greatest?
When it's closest?
Fantastic. Okay, so we're about to have a monumental freezing, okay? So when you have this small radius here, okay, this is Kepler's second law of equal areas, right? So when you have the smallest radius, that's when you have your biggest velocity. True?
Yes.
So out here, when you have this biggest radius, you have the smallest velocity. True? Ready to with this. So, here's the question. Colby, is my centripetal force constant now?
What did you say? Dropped it.
Okay, it's a good catch, by the way.
Thank you.
I always thought it was this flash. I don't have my glasses on either, so that helps. So here's the question. Is the centripetal force constant, or wait for it, does it change?
Change?
Oh, beautiful. Why?
Because the velocity and radius are changing too.
Beautiful, okay? So here's the question. So now we've established that the centripetal force is going to change. So Colby, is the centripetal force going to be greater when it's closest or when it's further away?
Further? Closer.
Why? When you're closer, what do you know about the velocity?
It's greater.
And that's getting squared, right? And it's on top.
Yeah.
And then you're dividing by a smaller
Smaller
radius,
radius.
right? So when Mercury is closest, okay, when Mercury is closest, you have two things going on that make the centripetal force get bigger. It's going faster, so your numerator is going to be bigger, and you're dividing by a smaller denominator, okay? So when Mercury is closest, it's going to take a lot of centripetal force, okay? So it's just like, imagine like you have a banister, okay? Like a bedroom banister or on the stairs, okay? And you grab a hold of that thing and you like slingshot yourself around, okay? That's going to take a lot of force because you're going really, really fast. So when Mercury is closest, when it's closest, your centripetal force is going to be that mass of Mercury. You're going to have a big velocity that's going to get squared, and then you're going to divide that by a small radius. And that's going to make that centripetal force need to get really, really big. Now, when you're further away, okay, so when it's at that point where it's way out there in that orbit, Caden, what's going to happen to the mass of Mercury?
Stay the same.
What's going to happen to the velocity?
Decrease.
So we're going to have a smaller velocity, but then what's going to happen to my radius?
Increase.
It's going to get bigger. So what's that going to do to my centripetal force?
Decrease.
Oh, so I'm going to have a small centripetal force when I'm furthest away, but I'm going to need a big honking centripetal force when I'm closer. Okay? Cool with that idea. Now, what's the source of the centripetal force? It's either a rope, a track, or gravity. Gravity. Oh, so this is where the magic happens. They go, wow, this is cool. When the planet is closest, you need more centripetal force. Cool, right? But What happens to the gravitational force when you're closest?
It increases.
Oh, it increases. So this is where this thing has to go hand in hand. It's like, right, we're closer. We need more centripetal force because we're going really fast with the small radius. So all we're doing today, Zach, is we're just finishing that. That's all we're doing, okay? And then also starting another discussion. So when Mercury is closest, you got to have all of this gravitational force, right? Because you need all this centripetal force because it's going really, really fast with a really small radius. Okay, it's like, oh man, gotta go really try to turn, okay, right? But now when it goes further out, everybody kind of chills out, right? Hey, we're a little slower, we've got a bigger radius, you know. That's kind of chilled out, right? I don't need as much centripetal force, but again, what happens to my gravitational force? It becomes weaker, okay? So this has to go hand in hand. I could not have that work in opposition. Like I couldn't need more centripetal force when I was closer and gravity become weaker, okay? That would be like, oh, I'm going to try and swing Hank the bowling ball, okay, around on the end of a little piece of cotton string, okay? It is not going to happen, right? Bad things are going to happen. So this is why these have to go hand in hand. When Mercury needs more centripetal force, gravitational force gets stronger. When Mercury doesn't need as much centripetal force, gravitational force weakens. Now, what if Mercury moved in a perfectly circular orbit? Would the gravitational force ever change? No, but guess what? What else wouldn't change?
Velocity.
Yeah, the velocity wouldn't change, so therefore the centripetal force wouldn't change. But because you're moving in an elliptical orbit, your gravitational force is always changing, becoming smaller or weaker, but then your centripetal force is also changing in that same situation. More centripetal force, more gravity, weaker centripetal force, weaker gravitational field. Okay, so this is why these just all form one by tapestry of ideas. And at that point, that was one of the big breakthroughs of science going, because Newton goes, wow, cool, this is why this works. And we goes, oh yeah, now we understand the gravitational role of this problem. Okay, so at this point, I'm about to turn you loose. So let's talk about question number 4. So this is question number 4 on the bottom of that 3rd page. So you want to calculate the gravitational force between Mercury and the Sun. So what I've given you is like the average orbital radius of Mercury. Okay, so on average, and obviously that's going to change, but on average, that radius is 5.8 times 10 to the 10th meters. So that's the distance from the Sun out to Mercury. Now, to give you some perspective, okay, that's 10 to the 10th. The distance from our Earth to our Moon is 10 to the 8th. This is 10 to the 10th. So the distance between Mercury and the Sun is like 100 times greater than the distance it is between our Earth and our Moon. Okay? So you kind of get like some perspective. Okay? So, even though it's the closest planet, it's still a long way from the Sun. All right? So, here's what I want you to do on question number 4. You're just going to use F equals big G, mass of Mercury, mass of the Sun, divided by R squared. Okay? There you go. Now, when you get to number 5, so that's what you're going to use on number 4. When you get to number 5, you're going to calculate the centripetal force needed to keep Mercury in orbit. Now, what we're going to assume on number 5 is that we're going to calculate the average amount of force. Okay? Realistically, that's always changing, but then we'd have to do calculus and do integrals over change in radius, and it's just going to get real, real ugly. So we're just going to make it simple. Okay? So what's going to happen on number 5, you're going to use that centripetal force equals mass 4 pi squared r over t squared. Okay? Now, here's the deal. Is that going to be the mass of Mercury? Or is that going to be the mass of the Sun?
Mercury.
Mercury, because that's what's moving around in the orbit, right? So you got the mass of Mercury, I gave you that up there. What units does that radius have to be in?
Meters.
Meters. Period has to be in
Days.
seconds. But I've given the period as,
Days.
now, when you convert those days into seconds, do not round the seconds, okay? Keep the full-blown number of seconds. Round this calculation when you get to the end. So you're going to do two calculations. This is going to get you the gravitational force between Mercury and the Sun. This is going to get you the centrifugal force needed to keep Mercury in orbit around the Sun. Hopefully, you should see a very simple relationship when you get done. Okay? So, at this point, you should have enough information and knowledge to fill out and answer that everything on that last page. Okay? So here's what I want when you get this thing done. So, you have, this is going to be page 1, okay, the lab itself, all right? Then I want the graph as the next part, that second page. But make sure you have a whole bunch of things on this graph. You should have 3 shaded regions. I should clearly be able to see a single point where it's going fastest, a single point where it's going slowest, a region where it's speeding up, a region where it's slowing down, okay? And then I should be able to clearly see 4 of those relative force vectors, okay? So, and again, don't make me try and sort through kind of like this hidden message thing to try and figure out what you've written. Highlight it, whatever, just make it big enough that I can easily see what you have going on. So, 3 regions, 2 points, 2 regions, 4 relative force vectors. Okay? Everybody cool with that? So that's what's going to be after the lab itself. Then you're going to hand in the data table, okay? And what I should be able to clearly see on this data table are the 3 regions that you chose to find the area, okay? The first one's going to be the same. Everybody, we all did December 20th to December 30th, okay? So that's going to stay the same for everybody. But then you want to highlight those other 2 regions, okay? So that so if there's an issue, I can go and find that area or those dates and know what you've done. That way I don't have to kind of guess, which ones are they looking at, okay? So, lab itself, graph, data table. Any questions? Going once, going twice, sold. So stop that for a second. And so no, you don't have any homework tonight. Okay. So now we're going to start this big, and this is going to take today and tomorrow to get through all these equations. All right? So.
Good news, bad news.
It's like good news, bad news day.
Kind of, yeah. Okay. So here's the deal. So let's say that Kelsey is standing on the Earth, obviously not to scale. Okay? And we want to calculate the gravitational attraction between Kelsey and this rock that we're on. So we're going to look at 3 different ways that we could potentially do this calculation, okay? 3 different ways, okay? Option number 1. At the end of Kelsey's right index finger, there's a strand of DNA. And within that strand of DNA, there's a nitrogen atom. And within the nitrogen atom, there are 7 protons and there are 7 neutrons, okay? So we're going to take the mass of one of those neutrons, which has a mass of 1.67 times 10 to the negative 27th kilograms. It's pretty small, okay? Mass of a proton is about the same. Mass of an electron is 9.11 times 10 to the negative 31st. Don't write this down. I'm never going to expect you to do this. It's just an academic exercise. But here's what I do want you to see. Is that notice that the mass of an electron is like 1,000 times less than the mass of a proton or neutron? Okay? So that's why I said like electrons. Remember when we did the static electricity? I said electrons are like the chihuahuas of the world. They go yip, 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 and they're really, really small. They're like 1,000 times less massive than a proton or a neutron is. But they have the same amount of charge. So anyway, so back to our story. So imagine the end of Kelsey's right index finger. There's a strand of DNA, there's a nitrogen atom, and there's a single proton that makes up that one atom, one proton, right there. Okay? So that one proton at the end of her finger is gravitationally attracted to every electron, proton, and neutron that makes up the Earth. Okay? So option number one, we're going to take that one single proton, and we're going to use F equals big G, the mass of that one proton, and we're going to say that, okay, directly underneath her chair, there is a proton that makes up the Earth. Okay? So that proton here is attracted to that proton there. So we're going to do that calculation. And then within the room that makes up the floor, there's all of these protons that make up, all the particles that make up the floor of this room. And then we're going to expand that. And we're going to calculate the gravitational attraction between that one proton and every proton, electron, and neutron that makes up the Earth. Okay? Because fundamentally that's what's happening. That one proton at the end of her index finger is attracted to everything that makes up the Earth. So we've got to know where these the mass of all these particles and where they are, because we have to know the distance squared. So we're going to do that computation for that one proton on the end of her finger with every particle that makes up the Earth. Now, if you remember, nitrogen, atomic number 7, has 7 protons. So we've got to do that for one proton, and then we've got to do that for the second proton, the third, the fourth, the fifth, the sixth, the seventh. Then there's 7 neutrons. Right. And we've got to do that for all the neutrons. And that's just one nitrogen atom and one strand of one DNA on the end of her right index finger. Okay? So then, but that's going to be different than the particles that make up her hair. Okay? Because those are up here, right? So that's going to be a whole different distance. So what we would have to do, and we're not going to do this because it would take a lifetime of lifetimes to even begin to do this computation, is sit there and go, wow, that's a lot of math. Okay? Because there's a lot of particles that make up Kelsey. There's a lot more particles that make up the Earth. And we'd have to do this again and again and again. But here's the conceptual part that's important that you understand, is that what creates your weight, okay, is that every particle that makes you up is gravitationally attracted to everything that makes up this Earth, okay? And that sum total is what creates weight, okay? So, on an atomic level, every part of you is attracted to every part of the Earth. We're just not going to do this because it would take an eternity to do all these calculations, okay? But conceptually, that's what creates weight. Okay, Brian, stop that. I will continue this.